The moon has remained relatively unexplored by the United States and NASA for quite some time, but there is a second space age coming. And with this new space age, regular Americans are excited and curious to know what lies beyond the bounds of Earth. This excitement in space and space exploration has taken a shift towards the moon. Team Luna hopes to contribute to this exploration with our proposed plan to send a rover to the moon by 2030 to explore multiple magnetic anomalies that could hold the potential for setting up life on the moon. This is the Lunar Uncovering Navigation and Aggregation mission.
The mission vehicles consisting of the orbiter tanker, lander, rover, and return vehicles will be launched by the SpaceX Falcon Heavy into direct lunar orbit. Once in lunar orbit, the lander carrying the rover and sample return vehicles will land on the lunar surface. The rover, which has been stowed within the lander, is then deployed in order to survey the site, take magnetic field measurements, and collect samples which operators have deemed candidates for acquisitions. The sample collection is performed using the EMI protected sample canisters in order to minimize contamination. Once in situ sample transfer has completed, the lander is designed to reascend back to low lunar orbit and dock with the orbiter. After docking, the lander is able to refill from the stored tanks of fuel and propellant within the orbiter. During this refueling process, the filled sample return vehicles are deployed and propelled back to the ISS. In addition, a heating procedure is performed on the lander legs in order to restore the energy-absorbing qualities of the shape memory alloy base shock absorber. At this point, this mission architecture is able to repeat with the same procedure.
The Rover Prototype was built over the course of a month. First was the purchase of all the materials we thought we needed to build this rover, including a model rover kit, robotic arms, electronics to control the rover, and wood for the testing setup. This was not a straightforward follow the manual type of assembly. Many challenges obstructed our goal of creating this prototype. The chassis that was planned on being used was originally too small, and so the idea came to 3D print 4 smaller plates and glue them together. However, this idea created a plate that was too flimsy to support the weight of the arms, so a bar connecting each plate was used to vastly improve the strength of the chassis. The 3D printing also presented an interesting challenge after a communication error occurred. This led to the slot on the wheel for the motor being too small. Fortunately, the motors came with rims that were able to be glued to the wheels so that the motor would fit properly.
Another big issue we faced occurred while testing the rover. When the rover was tested on concrete, it ran just fine. However, when we tried to run it on sand, the rover had no traction at all and the wheels sank the rover in. We believe this was due to the plastic material of the 3D printed wheels and the design of the wheels, since the surface area that was in contact with the sand was not large enough to prevent the wheels from sinking into the sand. The team immediately got to work on brainstorming ideas on how to solve the problem. The best solution we came up with was adding cardboard and sandpaper to the wheels to increase the surface area of the wheels and improve their traction. This instantly improved the mobility of the rover on the sand and allowed us to begin testing. However, testing showed that the wheels somewhat limited the mobility of the rover and still had room for improvement.
Once the rover was designed, built, and all the bugs and major issues were fixed, we had to create tests to find the limits of the prototype and determine its feasibility. The testing was done in a testing rig created to simulate the gravity of the moon on the rover. The testing rig worked by using a pulley system that moves along with the rover, while a positive vertical force is applied on the rover with weights that are proportional to the rover weight. On the moon, gravity is approximately 1/6 as strong as on Earth, thus the weight on the pulley was about 5/6 of the rover weight. Sand was also added to the enclosed testing rig to simulate the lunar surface that the rover would encounter. The first component of the rover that was tested was the speed. The motors were put at different voltages ranging from 3.5 volts to 12 volts, and the time to reach 49 inches was recorded. If the rover didn't move or reach the required distance due to slippage, that was also recorded. The slippage only occurred when the voltage of the motors was below 4.94 volts. The slowest speed that the rover could move without slipping was 12.92 inches per second, or 0.73 miles per hour. The fastest speed recorded was 31.62 inches per second, or 1.79 miles per hour. The second component of the rover's mobility that was tested was its ability to go over inclines. The rover had to get over a ramp inclined at angles ranging from 9 to 23 degrees. The surface of the ramp was also a tested variable, so a ramp with and without sand was tested. The rover had to reach the top to get a positive score. The largest angle that the rover could reach on the sanded ramp was 16.15 degrees. The largest angle that the rover could reach on the ramp with no sand was 20.65 degrees. Based on these results, it can be concluded that the wheel design is the biggest factor in the rover traveling at an incline. The robotic arms also had to be tested to ensure that they were able to accomplish their many tasks. Tests were conducted to move the arms in a variety of ways, including having the arms grab samples and deposit them in a container. The team found that the robotic arm movements did not have any impact on the stability or movement of the rover. The team has deemed that the robotic arms are feasible to be used on the moon.
Based on the results of the hardware testing, the lunar mission design will be revised and improved. New wheels need to be designed and constructed that will provide better traction on the loose lunar regolith. Additionally, the current wheel design kicks up a significant amount of sand and dirt, so some shielding will be added to protect the electronics, servos, and bearings on the rover. Despite these challenges, our rover prototype proves that our design has the potential to complete our mission on the lunar surface. Team Luna hopes that the science and exploration goals of this mission lead to uncovering many mysteries on the moon, and that unmanned rovers to the moon to achieve these goals become more common in the future.